This is a circuit, obviously, where everything is in series, and you will always remember twinkle, twinkle, little star, V is equal to IR. V is voltage, I is current, unit is amps, and R is resistance in ohms. Okay, so finding equivalent resistance in a series circuit, easy as falling down, okay? You can do this in your head. You don't need to write anything down because it's just the additive, it's the sum of the resistances. So the equivalent resistance here is 6 ohms. Fantastic. For the whole circuit, the voltage difference is equal to the current times the resistance. So we can figure out how much current is flowing through the whole circuit. Now here's the part that we hadn't really discussed before. That V is that potential difference, so it's the amount of difference in electrical potential between the positive and negative terminal of the battery. And we only deal with DC circuits because they're much simpler. We're not going to do AC circuits. If you go on to electrical engineering stuff, you'll have to deal with AC. More power to you. It's equal to the total current times the equivalent resistance of the circuit. Well, because this is all in series, the equivalent resistance is just the additive resistance across each resistor. Well, it's really the current in number 1 times the resistance of number 1. Current in number 2 times the resistance in number 2. But as long as we're dealing with a series, I'm trying to shrink this. All right, so really what we're saying is that that voltage is equal to the current in each resistor times the resistance. So for each individual resistor, there's current across the resistor, coming through the resistor. As long as they're in series, the current is the same throughout the whole circuit. So each resistor in series has the same thing. So it's just actually the total current times R1 plus R2 plus R3, etc. Okay? So the voltage, the potential difference overall is the total current through the system times the resistance. That's as long as we're in series. It is different with parallel. So once you guys get through the series problems, we'll talk a little bit more about parallel. Questions? Okay, so this is the 20B stuff. This is parallel resistors. We talked a little bit yesterday about the fact that 4 resistors which are in parallel, such as these fine resistors, yeah, that's the worst drawn resistor I've ever done, such as these, if you have a 2 ohm resistor and a 2 ohm resistor, the resistance here is not 4 because the equivalent resistance of resistors in parallel is actually 1 over R1 plus 1 over R2.
Why can't you just do 1 over R1 plus R2?
Well, algebraically you can, but this is the root here.
So it'd be 2 over...
So 1 over 2 plus 1 over 2 is 1. This would have an equivalent resistance of 1. Yeah. No, it's 1. Hold on. So you get 1 over 2 plus 1 over 2 equals 1. So 1 over 1 is 1. 1 is its own reciprocal. Okay, that's great. Now, what that means is if you've got resistors that are, like if you had identical resistors, just for instance, not related to any particular problem that's assigned. Yeah. It's kind of looking like it, isn't it? Zip, 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 zip. So if you have a bunch of equivalent resistors and you know that they're identical and you know the equivalent resistance of the circuit, can you find the resistance of one of the individual ones? Of course you can. Gesundheit. 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. I have to move this down. Plus 1 over R4. But if those are identical, that's actually just 1 over R equivalent equals 4 times 1 over R1. Because if they're identical, it's just that. At that point, if you have this, can you solve for this algebraically? Yeah, of course you can. So you can find the individual resistance of each of those individual resistors. That will help you with number 2 in 20B. Now let's talk real briefly about Okay, so you can solve for the resistance of the individual pieces. Remember that when they were one wire, of course, they were essentially in series with one another. So you have to do that as a series thing, and you can find the resistance of the whole piece of wire. Okay, let's talk a little bit about voltage and current in parallel circuits. All right, so let's talk a little bit about who here is done with 20B? Are you done with 20B?
I'm on number 2.
Okay. I'm just going to do my spiel for those who are not here. Okay, so in a circuit where we have parallel resistors, our computations for voltage and current are a little bit different. In a series situation, the current is the same across all of them. In parallel, it's not. And if you think about this sort of logically, if we go back to the water metaphor, when you have two pipes, if you have a little tiny pipe here and a giant pipe here, I didn't draw that very well. Well, anyway, there we go, that's better. Water's going to flow where it's easier to flow. So you're going to have higher current in the place with lower resistance. So the resistance is still, the equivalent resistance over the whole circuit is the 1 over R equivalent plus 1 over R2, etc. But the current is actually a sum. So the total current in the circuit is I1 plus I2 plus I3, etc., for as many resistors as we have, because it is going to be different in each one. So the total voltage divided by the equivalent resistance gives you your I total. Well, what this allows you to do is, if you know, and the voltage in a parallel circuit, the voltage is the same throughout. So the voltage across one resistor is equal to the voltage across the second resistor is equal to the voltage across the third resistor. Voltage never changes, current does. In a series circuit, the current never changes. We haven't gotten to calculating voltage across the individual resistors yet, but so when they are in parallel, this is true. Well, what that means is that the individual current is equal to the total voltage divided by the resistance of the individual resistor. Pretty easy. That's what you already figured out, I assume. Okay, that's it.